Welcome back, everyone, to another deep dive. This time, we're going to be exploring the nano world.
Really fascinating stuff.
Yeah, getting down to the itty-bitty gritty.
Yeah.
The nanoscale.
Yeah.
So we've got a whole stack of research here to help us try to uncover what's going on down at that level.
You know, it's interesting because these things are so small, you can't even see them with the naked eye.
Right.
So we have to rely on all these different instruments and techniques
To characterize.
to even know what they look like and understand their properties.
Yeah, it's kind of like, if you think about it, you can't really understand how a car works
Right.
unless you know what the engine looks like.
Exactly.
The wheels, all the different components.
Exactly. It's like trying to understand a complex machine without a parts list.
Yeah.
And so characterization is really like providing that parts list for nanomaterials.
So let's talk about what are some of the tools that we have
Okay.
to,
Great.
do this characterization.
One of the most powerful tools that we have is the electron microscope.
Okay, so we're talking microscopes now.
Yeah, but not the kind that you used in high school biology class.
Right.
This is
Not the one from my childhood.
Yeah, not the one from your childhood. These are very specialized instruments that use beams of electrons instead of light.
Why electrons?
Because electrons have a much shorter wavelength than visible light, and that allows us to get much higher resolution.
Ah.
So you can imagine, you're trying to look at something that's nanometers in size, visible light. The wavelength is just too big. It's like trying to measure the width of a hair with a yardstick.
Yeah.
You need a more precise tool, and electrons give us that precision.
So electrons are our tool for the nano world.
Yeah, exactly. There are eyes into the nano world.
And we have different types of electron microscopes, right?
Yes. So two of the most common types are the scanning electron microscope, or SEM,
Uh-huh.
and the transmission electron microscope, or TEM.
Okay, so let's break those down one by one.
Okay.
SOM, what is that all about?
So S is really about looking at the surface of a material in very high detail. So you can imagine you're getting an aerial view of a landscape.
Wow.
You see all the mountains and valleys and the rivers and
Right.
the trees. SEM does the same thing for a nanomaterial. It lets us see all the bumps and grooves and the shapes and the structures.
Oh, so we're looking at the topography then.
Exactly. We're looking at the topography of the surface.
So if we wanted to see, the really, really fine details on like a butterfly wing,
Right.
we could use SEM to do that.
Exactly. You could see, the individual scales on a butterfly wing. You could see the tiny hairs on an insect's leg.
Yeah.
You can see all sorts of amazing things.
Wow, that's pretty neat.
Yeah.
So SEM is all about the surface. What about TEM? What's the difference there?
So while SEM lets us see the surface, TEM lets us see through material. So it's
Okay.
like taking a cross-section. You're actually looking inside the material.
Wow.
To do this, we need to make the samples incredibly thin, sometimes just a few atoms thick, so that the electrons can actually pass through them.
Wow, that sounds really delicate.
Yeah, it's a very delicate process preparing samples for TEM.
So what kind of information does TEM give us then?
Well, TEM can tell us the size and shape of nanoparticles. It can tell us how the atoms are arranged inside a material.
Uh-huh.
It can even tell us if there are any defects or imperfections in the material.
So you're talking about like little tiny cracks.
Yeah, tiny cracks, little voids, missing atoms, those sorts of things.
Interesting.
And these defects can actually have a big impact on the properties of the material.
How so?
Well, for example, a defect in a semiconductor material can trap electrons,
Uh-huh.
and that can affect how well it conducts electricity.
That's fascinating.
So,
So TEM is not only letting us see the structure,
right.
but it's also giving us clues about how the material behaves
Exactly.
because of that structure.
Right, because of that structure.
That's really neat.
And there are even more specialized types of TEM, like high-resolution TEM or HR-TEM.
HR-TEM sounds pretty intense.
It is.
What is that?
Yeah. So HR-TEM uses a very coherent electron beam and some sophisticated image processing techniques to actually achieve resolutions down to the atomic level.
Whoa. Oh,
So
level.
we can literally see the individual atoms
Right.
in a material and how they're arranged.
That's incredible.
Yeah, it's like having a microscope that's so powerful you can see the individual Lego bricks that make up a building.
Wow.
Oh.
That is really amazing. What kind of insights can we get from that level of detail?
Well, HR-TEM is really important for understanding how the arrangement of atoms affects the properties of a material.
Okay.
So, for example, different arrangements of carbon atoms can give us materials that are as different as diamond and graphite. Right, diamond is the hardest known natural material, and graphite is very soft.
Yes.
You use it in pencils.
And bear.
And that difference in properties comes down to how the carbon atoms are arranged, and HR-TEM allows us to see those arrangements directly.
So we can actually see why diamond is so hard
Exactly.
at the atomic level.
At the atomic level.
That's pretty amazing.
And we can see why graphite is so soft at the atomic level as well.
So is that like kind of the limit? Then can we go any
Right.
deeper than the atoms or?
So there are other variations of TEM.
Uh-huh.
For example, there's something called scanning transmission electron microscopy, or STEM.
STEM, what's that about?
So STEM is kind of like a hybrid between SEM and TEM.
Okay.
So instead of illuminating the entire sample at once, like in conventional TEM, STEM focuses the electron beam down to a very tiny spot, and it scans that spot across the sample.
Okay.
And by doing that, we can get information about the composition of the material
Okay.
with very high spatial resolution. So it's like we're taking a chemical fingerprint of the material point by point.
Wow.
So this is really useful for analyzing materials that are not uniform in composition, where you might have different elements clustered in different regions.
Okay.
We can actually map out the distribution of elements and see
Wow.
which elements are next to each other. And
So that would be really useful then for things like alloys or
alloys.
Composites.
Composites, exactly, where you have different materials mixed together.
Yeah.
You really want to see how they're distributed at the nanoscale.
Wow. Okay, so we've got SEM for looking at the surface, TEM for seeing through materials, HR-TEM for really getting down to the atomic level detail, and then STEM for mapping out the composition.
Right.
It seems like electron microscopy is like a real Swiss Army knife for nanomaterial characterization.
It really is. It's a very versatile tool.
That's amazing.
But it's not the only tool that we have.
Okay.
Another powerful tool is X-ray diffraction, or XRD.
XRD. So now we're talking about X-rays, not electrons. What's the difference?
So electron microscopy relies on the interaction of electrons with matter. XRD uses X-rays to probe the internal structure of a material.
Oh, okay.
And it's particularly good at revealing how the atoms are arranged in a crystal lattice.
So it's almost like taking an X-ray then.
Yeah, it's like taking an X-ray of a material to see its internal structure, its skeleton, so to speak.
And why is that important to know how the atoms are arranged in a crystal lattice?
Well, the arrangement of atoms dictates many of the properties of a material.
Okay.
So its mechanical strength, how strong it is, its electrical conductivity, whether it conducts electricity well or not, its optical properties, how it interacts with light. All of these things are affected by how the atoms are arranged.
So even small changes in the arrangement can have big consequences.
Exactly. Even very subtle changes in the arrangement of atoms can have a dramatic impact on the properties of a material.
Do you have an example?
Yeah, so let's take titanium dioxide, or TiO2, as an example.
Right.
TiO2 can actually exist in a few different crystalline forms, including anatase rutile and brookite.
Okay.
And each of these forms has a different arrangement of titanium and oxygen atoms, and that leads to different properties.
Okay.
So, for example, anatase TiO2 is a very good photocatalyst,
Okay.
which means it can use light to drive chemical reactions. Rutile TiO2 is more commonly used as a white pigment in paints and sunscreens.
Wow, that's pretty cool. So by using XRD, we can figure out, okay, which type of TiO2 do we have?
Exactly.
That will give us a clue as to what it can do.
Exactly. We can look at the XRD pattern and say, this is anatase TiO2, so we can expect it to have good photocatalytic properties, or this is rutile TiO2. We can expect it to be a good white pigment.
That's fascinating.
Yeah. And XRD can tell us other things as well.
Okay.
Like the size of the crystals in our material, whether there are any defects in the crystal structure, and even how much strain the material is under.
Strain meaning like it's being pulled or pushed in a certain...
Exactly. It's being stretched or compressed.
Okay.
And that can actually affect its properties as well.
Wow. So XRD is a really powerful technique.
Yeah. It gives us a lot of information about the internal structure of materials.
Okay.
Especially crystalline materials.
Great. So are there any other tools that we use to characterize these nanomaterials?
Yeah, so another important technique is X-ray photoelectron spectroscopy, or XPS. XPS.
Okay.
So unlike XRD, which probes the bulk structure of a material, XPS is all about the surface.
Oh.
It tells us about the elemental composition and chemical states of the atoms on the very top layers of a material.
So it's like taking a fingerprint of the surface.
Exactly. It's like taking a chemical fingerprint of the surface, and this is really important because at the nanoscale, a large proportion of the atoms in a material are actually on the surface. So the surface chemistry plays a huge role
Makes sense.
in determining the properties of the material.
So it's not just about what it's made of.
Right.
It's also about how it interacts with the world around it.
Exactly. And XPS can tell us things like which elements are present on the surface, what their concentration is, and even their chemical state.
Chemical state meaning?
So, for example, we can tell if a carbon atom is bonded to another carbon atom, an oxygen atom, or a metal atom, and that will affect its properties.
So we can actually tell what kind of bonds the atoms on the surface are forming.
Exactly. We can see how they're interacting with their neighbors, and that gives us clues about how the material will behave in different environments.
That's incredible.
Yeah, it's a very powerful technique for understanding surface chemistry.
So it sounds like we've got a lot of tools here for understanding the nano world.
Yeah, we have a whole arsenal of tools.
From electron microscopy to X-ray diffraction.
To X-ray photoelectron spectroscopy.
XPS, yeah.
There's a whole suite of techniques that we can use to characterize these materials.
And we haven't even talked about BT.
Oh, right. BIT is another important one.
What is that about?
That's for measuring the surface area of a material.
And why is surface area important at the nanoscale?
Because as we shrink materials down to the nanoscale, their surface area to volume ratio increases dramatically. So that means a larger proportion of the atoms in the material are exposed to the surrounding environment, and that makes them more reactive. So surface area is a really important factor in determining how a nanomaterial will behave.
So the more surface area, the more reactive it is?
In general, yes.
Okay.
There are always exceptions, but that's a good rule of thumb.
That's interesting.
Yeah. And this enhanced reactivity is what makes nanomaterials so interesting for things like catalysis sensing, drug delivery.
Right.
All sorts of applications where you want the material to interact with its environment.
But we need a way to measure that surface area.
Right, and that's where BEAT comes in.
Okay.
BT stands for Brunauer Emmett Teller, who are the scientists who developed the technique. And it relies on the adsorption of gas molecules onto a surface. So you basically have a container filled with a known amount of gas, usually nitrogen. And you introduce your sample into that container, and some of the gas molecules will stick to the surface of the material. The more surface area the material has, the more gas molecules it can absorb.
So by measuring how much gas is absorbed, we can figure out the surface area.
Exactly. And we do this by varying the pressure of the gas and measuring the amount of gas absorbed at each pressure. And then we use an equation called the BT equation to calculate the surface area from that data.
The BT equation sounds complicated.
It's a bit complicated, but the important thing to understand is that it relates the amount of gas absorbed to the surface area of the material.
So the more gas, the more surface area.
Exactly. So BT is a really important tool for characterizing nanomaterials because it tells us how much surface area they have.
Right. And we know that surface area is really important for determining how reactive they are.
Exactly.
Wow. We've covered a lot of ground already.
Yeah.
From electron microscopy to X-ray diffraction to XPS and BT.
We've covered a lot of different techniques.
But I'm eager to hear more
about
how they all fit together to really give us this full picture of what's happening in the nano world.
Yeah, let's dive in a little deeper to some of these techniques. Yeah, it really is amazing how all these techniques come together, and they give us this deep understanding of materials at such a tiny scale.
Yeah, it's like, we've shrunk ourselves down to the size of an atom and can now see everything that's going on.
Right, exactly. And before we move on, I want to circle back to XPS for a moment. Remember we talked about how it can tell us about the chemical states of elements on the surface?
Yes. You mentioned, being able to tell if a carbon atom is bonded to, like, another carbon, an oxygen, or even a metal.
Right. And the key to that is something called chemical shift.
Chemical shift.
Yeah. So the binding energy of an electron in an atom is slightly influenced by its chemical environment.
So what does that mean?
So you can kind of imagine the electrons in an atom as being held in place by a tiny spring. And the strength of that spring, or the binding energy, depends on what other atoms are nearby and how they're pulling on those electrons.
So like if a carbon atom is bonded to an oxygen atom, the oxygen is kind of pulling on the electrons of that carbon atom.
Exactly. And that pull changes the binding energy of the carbon's electrons.
Okay.
And this change in binding energy, this chemical shift, shows up in the XPS spectrum. And it allows us to distinguish between carbon atoms that are in different chemical states.
So we can actually tell what that carbon atom is bonded to
Yeah,
just
exactly.
by looking at its electrons.
Just by looking at how tightly those electrons are held in the atom.
Wow, that's pretty amazing.
Yeah, it's a really powerful technique.
So it gives us information not only about what elements are there, but also what they're bonded to.
Exactly. It tells us about the chemical environment of each atom.
Okay, wow. So that's XPS and chemical shift.
Yeah.
Now, what other techniques do we have for characterizing nanomaterials?
Well, remember we talked about how beat helps us measure the specific surface area of a material?
Yeah, you mentioned that it involved using gas molecules to, probe the surface.
Right. So beat relies on the principle of adsorption, which is the tendency of gas molecules to stick to a solid surface.
Okay.
So imagine you have a container filled with a known amount of nitrogen gas,
Okay.
and you introduce a sample of your nanomaterial into that container.
All right.
And some of those nitrogen molecules will stick to the surface of the material.
Okay.
They form a thin layer, and the more surface area the material has, the more nitrogen molecules it can absorb.
So by measuring how much nitrogen is absorbed, we can figure out how much surface area there is.
Exactly. And we do this by varying the pressure of the nitrogen gas
Okay.
and measuring the amount of gas absorbed at each pressure.
Uh-huh.
And then we use a special equation called the BT equation
Okay.
to calculate the surface area from that data.
The BT equation
Yeah.
sounds pretty complicated.
It is a bit complicated, but you don't need to know the details of the equation itself.
Okay.
The important thing is that it relates the amount of gas absorbed to the surface area of the material.
So the more gas that sticks to it,
Right.
the more surface area there is.
Exactly. So BEAT is a really important tool for characterizing nanomaterials because it tells us how much surface area they have. And as we discussed earlier, nanomaterials have a much higher surface area to volume ratio than bulk materials.
Right.
And this high surface area is what makes them so interesting for so many different applications.
You mentioned earlier that a catalyst with more surface area
Yes.
would be more effective because there are more places for the reaction to happen.
Exactly. A catalyst with a high surface area will have more active sites for chemical reactions to take place.
And is that kind of a general principle then, or is that specific to catalysts?
It's a fairly general principle. The more surface area a material has, the more it can interact with its surroundings.
Yeah.
So that's important for things like sensing, where you want the material to be able to detect very small amounts of a target molecule.
Right.
And it's also important for drug delivery, where you want the material to be able to carry a large amount of a therapeutic agent.
Okay, that makes sense.
So BEAT is a really valuable tool for understanding and optimizing the performance of nanomaterials.
That's fascinating. So it sounds like we've got XPS, which tells us about the bonding and the surface chemistry, and BEAT, which tells us about the surface area.
Right.
And we've got all these microscopy techniques for actually seeing the structures.
Exactly. I've got a whole toolbox of techniques.
You're really starting to get a handle on this nano world.
Yeah, we're starting to unravel its secrets.
It's pretty incredible to think about all this hidden complexity.
It really is, and we've only just scratched the surface.
Oh, no.
There's so much more to explore
Yeah, boy.
in the world of nanomaterials characterization.
There's much to learn about the nano world.
Oh, there really is. And it's interesting because these characterization techniques, they don't just tell us what a material is, but they also give us insights into how it behaves and how we can use it.
Yeah, and how we can control it and manipulate it.
Yeah. Exactly. And that's what makes it so exciting because, we're not just passively observing, we're actually learning how to engineer these materials at the nanoscale to do amazing things.
And we've got a whole arsenal of tools at our disposal, right from electron microscopy to X-ray techniques.
Right. And we're constantly developing new tools and refining existing ones. So it's really a rapidly evolving field.
And speaking of amazing tools, there's one more technique that I want to touch on that really kind of takes our vision to the next level, and that's high-resolution transmission electron microscopy, or HRTEM.
Oh, yeah. HRTEM is really incredible.
So we touched on it briefly before when we were talking about TEM in general, but what makes HRTEM so special?
So HRTEM is like the ultimate zoom lens for the nanoworld. It allows us to see the arrangement of atoms within a material with incredible clarity. It's like being able to see the individual bricks that make up a building or the precise arrangement of atoms in a crystal lattice.
That's mind-blowing. So how does it actually work? We're talking about things that are, smaller than the wavelength of light, right?
Yeah, right. Exactly. So that's why we use electrons instead of light. HRTEM takes advantage of the wave-like nature of electrons. So when we shine a beam of electrons through a very thin sample, the electrons interact with the atoms in the material, and they create interference patterns.
Interference patterns, like, when you drop a pebble in a pond and you see those ripples spreading out.
Exactly. Those ripples or interference patterns carry information about the spacing and arrangement of the atoms in the material. And by carefully analyzing these patterns, we can create images that show us the atomic structure in incredible detail.
So we're basically using the waves of electrons to map out the atomic landscape.
That's a great way to put it. It's like using sound waves to create a map of the ocean floor. We're using the waves to probe the structure of the material.
That's pretty amazing. And with HRTEM, we can actually see things that are just impossible to observe with other techniques, right?
Yeah, absolutely. We can see individual atoms, we can see the defects in a crystal lattice, we can see the boundaries between different materials, and we can even see the distortions in the lattice caused by strain or impurities.
That's incredible. Why is it so important to see these things at such a fine scale? What kind of insights do we gain from that?
Well, HRTEM is crucial for understanding the relationship between a material's structure and its properties. So, for example, a single atom out of place in a crystal lattice can weaken a metal or change the color of a gemstone. So by seeing these atomic scale defects, we can start to understand how they influence the material's behavior.
So it's like having X-ray vision for materials.
Yeah.
We can see the hidden flaws and imperfections that affect their performance.
Right, exactly.
Yeah.
It's like being able to see the cracks in a bridge before they become a problem.
So it sounds like HRTEM is a really powerful tool for material science.
Oh, it absolutely is. It's helping us to design new materials with improved properties, understand how materials fail, and develop new manufacturing processes that control the structure of materials at the atomic level.
This has been an amazing journey. We've explored a whole suite of techniques for characterizing nanomaterials from the surface to the atomic level. We've seen how electron microscopes give us visual insights. We've learned how X-ray diffraction unveils the hidden architecture of crystals and how XPS reveals the chemical secrets of a material surface. And we've explored how BET helps us measure the vast surface area that makes nanomaterials so reactive.
And it's all about connecting those different pieces of information, to get a complete picture of the material and how it behaves.
Yeah, it's clear that characterizing nanomaterials is not a one-size-fits-all approach. It takes a combination of techniques to really understand these complex materials.
Absolutely. And the more we learn about nanomaterials, the more we realize how much more there is to learn. It's a field that's constantly evolving with new techniques and instruments being developed all the time.
That's what makes it so exciting, though, right? There's always something new to discover, always a new challenge to tackle.
Exactly. And as we push the boundaries of what we can see and understand at the nanoscale, we open up new possibilities for creating materials with amazing properties and capabilities.
It's an incredible field, and I'm so glad that we got to dive into it today.
Me too. It's been a pleasure sharing this journey with you.
And with all of you listening out there, thank you for joining us on this deep dive into the nano world.
We hope you've enjoyed the journey as much as we have.
And remember, the next time you encounter something small, think about the incredible complexity hidden within a whole universe waiting to be explored.
Who knows what amazing discoveries await us in the nano world?